first up, as always, someone has to be looking to hire. Oh, yeah, there you go.
Hi, Michael from Presbyterian Hospital. We're looking to hire 2 people at the moment, and more to come in the near future. So if you're interested in working on healthcare and operations, a whole bunch of really interesting problems, come see networks.
And job posters will hang up at the TV. The giant TV over there. Cool. All right. Next up, the pizza bowl. bit.ly/pizza bowl. This came from Cabela's around FIT. So Cabela's. So go to bit.ly/pizza bowl and rate the pizza excellent, good, average, poor, never again. So make sure you want to keep collecting this data. It's very important. And it's legal. We play with the data. Thomas Levine can't be the only person playing with the data. Next up, we have the t-shirt. Anyone wants the NYC Data Mafia t-shirt? Where is it? Where's my mom? Where are you? Or IR New York. That's a great holding job. Oh, there you are. I was looking for you. Stand up. Yeah. You want one of these shirts? Or what James Lim at NYC Data Mafia? Come over here, talk to Joe, who's outside. We'll sell you one for $20. Next up. Next week we have a STAN class. Who here uses STAN? Who here wants to use STAN? Everybody. So we have a STAN class next week. A few of you are already signed up. You're coming. I think it's another one of those people. If you want to come next week, it's Monday through Wednesday, and there's a discount code NYHackR. So 20% off use that discount code next week. August 25th and 24th is JupyterCon. I know that's not as popular in this community, but they do have R support, they have Lua support, they have Python support. You can run Go and Jupyter now. And I'm sure there's other languages you can do as well. So that's August 21st and 24th. If you want a discount to that, it's NYOSP20. Open statistical programming. So if you want that. In September 13th through 14th, here we have the Carrot class taught by Max Kuhn, the author of Carrot. That's September 13th through 14th. That discount code is NYHackR. We have a lot of things going on. Strata is September. These are the wrong dates. Strata is in September. It might be the 11th through 13th, but don't quote me on those dates. The discount code for that is NYOSP20. You don't need to remember these. They're all on the message boards, and I will send out more emails. But the big news for us is, who went to the New York R Conference any of the past 4 years? All right. We are launching, finally in November, the DC R Conference. Yeah. One of our speakers is right here. You didn't know that until right now.
I've been looking forward to this. Thank you for the heads up.
Absolutely. That's how you get people to speak. You just announce in front of everybody. It's going to be November 8th through 9th in Washington, D.C. Super excited to be expanding to other cities. The website went live about 2 hours ago. So we're very happy. You're the first to hear that this is actually really happening now. And of course, NYHackR is a discount code. After this, we're going to go to the bar. We're going to Rye House. You know what's happening at Rye House? Katie, Paul. Where's your phone? All right. We're going to the Rye House. So after we thumb the meetup, follow them to Rye House. And as soon as the meetup's done, we're all going to the bar so we can clear out. All right. With that, I present you our next speaker coming all the way from Berlin to talk to us about composing functions together. Eugene.
Thank you. Thanks everyone for coming out. And oh, am I not on?
All right.
No, am I? Oh, okay. Yeah, thanks for coming out, and thank you, Jared, for inviting me, or giving me this opportunity to talk. So maybe I should say something about myself, because I'm sure no one has any idea who I am. I've been to the meetup twice before. So as Jared said, I'm coming from Berlin, and I'm here in New York for a couple of months at a place down in Lower Manhattan called the Recurse Center. It's kind of like a programming retreat. So I've been doing some R stuff, Haskell, and some mix of the two. And I think we'll see a bit of that today. I'm a mathematician by training, although I don't work as a mathematician now. I was working in Berlin as a data scientist, and we'll probably continue along that line. So this talk is not going to be very mathematical, but it has like a lot of mathematical elements in it. But it will be very, very practical and very. So I think we're going to have a lot of doing things and learning things together. So there'll be some familiar things, and I think maybe some new things, and hopefully something that you can use in your own work and fun. Because I actually use R mostly for fun. I'm not doing any work right now. Okay, so composing functions with Gestalt. So Gestalt is a package that I wrote. And actually, a new version went up on CRAN just today for the meetup. And this is this is the topic that I'm going to talk about: composing functions. So So I want to start with the basics, like what is going on? What do I mean by composing functions? Because it's the senses of the word. So one is composing in a mathematical sense, just chaining them together, doing one function another, and so forth. And the other is composing in the sense of writing, like composing prose, so writing functions. So we're going to talk about both aspects because they have a lot to do with each other. And even if you think, okay, well, I just want to do my work, this is actually very relevant to whatever you do because it's something you do all the time. You're always doing this. Even if you work primarily interactively. And so there are not going to be too many slides. Mostly I'll just be doing things live. It'll be what I didn't practice so much. But I think the fact that I didn't practice is a testament to the stability of the idioms that I want to present. Okay, so first, calling functions. Okay, this is something related to composing functions, but much simpler. So, well, what's calling functions about? So calling functions is something which this thing called the pipe, is in a package called magrittr, offers, and it lets you basically apply a function from right to left. From right to left. And the way it works is like this. You write a value and you pipe it to a function. And what this means is you're applying x as the first argument and then y as the second one. So it's just like a very convenient way of writing code that reads in the natural order. And you can go on with this. You can pipe one value to a function. That's a value, and then you can pass that on to another function. So g is another function, and the way it works with these operators is always that they associate to the left. So first you do this, is what I showed in the previous slide. So you apply f, and then you pipe that into g, and you have that. Okay, and you can imagine you can do very long chains. So I think most people are very familiar with this because it's very heavily promoted in tidyverse, and for good reasons, because it's a very concise way to write your code. And one thing I should mention here that's probably it's kind of obvious if you use this a lot. This see, the f has the two arguments, right? But in the bottom, but in the top there's just one. So the rule is always that somehow the first argument plays a special role. And this is very convenient because a lot of functions kind of are set up that way. Okay, so this is the pipe, and that's how you use it, and it's really wonderful. So the next topic is love, because everyone loves the pipe. It's a very powerful tool. It's something you don't have in Python. It's kind of actually a kind of a secret weapon of R in this area of interactive analysis. And once you start using the pipe, you find like uses for it everywhere. So very common as you look at code and has like pipes all over the place. And if you use pipes before, that's great because you know what's going on. You can do that at the console, you can put in the functions, and everything's great, pipes everywhere, wonderful. But then you use it, it's like anything you have too much of. It can be, it's not always good for you, right? Like too much ice cream is probably not good for you, although ice cream is also really wonderful. So if you use this long enough, at some point you will notice some pain points. Like either you will get like an error, a huge stack trace, and you don't know what's going on, or your code is somehow mysteriously slow. And you suspect it's not because you wrote bad code, but something mysterious is going on. Okay, so what's going on? So let's look at this again. So one thing to keep in mind is that when you pipe things, the things on the left and the things on the right, they are not the same things. Okay, it looks like it's one thing happening, not always the same object in play, but it's the thing on the left is a value and the thing on the right is a function. So to make it clearer, another way to write it is like this. You take this x and you pipe it into a function. So this dot pipe fg, this is the magrittr syntax for little function which is, has one argument, this dot. That dot is like a placeholder, and it sends, and it does what x may go back. So like what x is doing here in this line is what the dot's doing here. Okay, so you see there's two separate things going on. One is you're composing a function, that's the thing on the right-hand side in the brackets, and the value that gets pushed into it. So this dot, that dot doesn't do anything. It's just kind of a trigger. So it's, in some ways it's sort of hiding what the real issue is here. So what's the real issue? What you're actually doing is somehow the dot is just saying now compose. So why don't you just write that? You know, you just compose. So just make up some operator. So you can go back and just to see. So I purposely animated this. You can see like, okay, the dot disappears. So basically you're just highlighting what's actually going on. And the x, in fact, is a dummy variable because the x is the thing that varies. Okay, so x is also a dummy variable. So what you're left with is just the thing that's doing stuff, the function. So my starting point was actually like writing this kind of pseudocode. And I started like basically writing on paper or like typing in the editor. Like I want to be able to have this express this kind of thing. I don't want to write this dollar of the x. Okay. So this operator with this triple arrows is a function compositor. So it takes two functions and it composes them. So you do one function, another one. And it's an operator that you can install from this package called Gestalt. So Gestalt is one of those words that actually has a meaning in English which is kind of close to what it means in German, and it basically means a form and structure, and also has a connotation of something being integrative. Okay, so you think of it like that. So that's why it has this name. And so it's, first of all, it's not a pipe. Okay, so it's sort of so it's coming from the syntax of the pipe. So kind of fool's errand would be to say, okay, magrittr is wonderful, but I want to do something else, and I'm going to make up my own notation, and you guys come along with me. Forget that. No one's going to do that. So that's kind of, the symbol is like a pipe, but there's more of them, sort of to make it visually distinctive. It has a similar syntax, but it's doing something quite different. So it's not a pipe. What is it? Okay, so I'm going to get now, okay, so that was the background. The rest of the talk is going to be mostly me in our studio doing stuff. Like I said, I hadn't practiced this very much, so there could be crashes. You ready? Should we do this? I guess I don't have a choice. So. Yeah, okay. All right, okay, so let's do, also the reason I want to do it, not just that I was too lazy to make slides, I think it's very useful to see, like, you see code like on a blog or something, or like in a package, and you don't really get an idea of like how that was built up. So the thing I want to impress, even if you kind of like forget the details, is sort of the, like, how do you go about moving around in your code and objects? Okay, so that's the reason I'm doing this, not because I was too lazy, really. Okay, so I'm going to load up these two packages. So just to give you just a reminder, so the way the pipe works is you can take, so for example, logarithm of 2 is this number, but you can write it like this. Right? This is what I wrote before. Actually, you can just write logarithm, right? And you can compose, let's say you can do -2, oops, the logarithm, like absolute value, and then logarithm. So that will take absolute value 2 and then logarithm. Okay, same thing. Now, so that's how piping works, very, very simple. So how does this, this composition works? Well, we had this, right? So basically, okay, if I write what I had on the slide earlier, it's this, right? So that thing in the brackets, this is a function, okay? So you can just write that function directly with this pipe operator, or, sorry, I hope I don't say that again. This compositor. I have to, oh, if you have a good name for this, please tell me, because I actually don't just type it, I never, compose. Okay, compose. So I will come back to this. So there is, just a quick side remark, there is a package called Pro that I think most people are familiar with, and it has a function called compose that does composition. But I want to show, I hope that I demonstrate with this example is that that function is doing things in the wrong order, like in a very inconvenient order. So it's like compose, but everything is going from right to left. Just like piping is from right to left. Okay, so this is a function. So if you print it out, it has two parts, the absolute value and logarithm. And you can apply, say, -2 to it. Okay, so that's how it works. And you can string as many functions as you want. Okay, let me do like two simple like toy examples just to show how this works. So make a function called Scramble, and what it's going to do is it's going to sample a bunch of points, and then it's going to join them together. So collapse. So it's some function. So if you write it out, print it out. Okay, well that's a little bit long. The first function is this sampling, and the next one is pasting. So if I send in like so letters. Okay, that's built in. So if I scramble letters, it will just mix them up and paste them together. If I can scramble, say, just 5 of them. Like, oops, no, size, it's called size. So now I took 5 letters, and I run it again. It's random. So every time it's a different example. That's fine. Okay. I could have done that with any number of ways. I could have even written it by hand. So I wanted to show you two things here which are interesting. So one is if you look at the Scramble, the formals, like what are the arguments? Like what does the function look like if you're coming in from the outside? Okay, it has the same formals as the sample. Okay. So if you did the same thing with this magrittr pipe, what was it, paste, collapse, you just get value. So you lose all of this. Okay, because it comes just a function of one variable. So I cannot do, for example, if I ran this thing, right, fine, I can do letters, that's okay, but I just want to do 5 of them. No, it doesn't work. So the one thing is it preserves what a function looks on the surface. And the other thing is you can, like, if I run it, it does something, right? So this is a very simple thing. And if I print it out, you can see what it's doing. okay, what if we could not look at this code? Let's just look at like what results it's producing in the middle. So what you can do is you can write another function, which is going to be a function on function. So it's going to transform function. So it's easier if I just write it out and then explain how this works. So you, oops. Compose, so this is a compose. So there's a compose function in Gestalt, and it does composition, but in left to right order. So this is a function. If you write it, you print it out, it does two things. It does this apply, compose, print, and then compose. That's the second thing. Oh, actually, so a lot of times, like you print stuff out, like number 2, the second function is just like the source code. What is that? So sometimes you can just give it a name, or give it a name, compose. So if I write, so now it says compose, so you have some idea what it is. And what you can do is, I'm just going to write out, show how it works, and then explain like what is it doing. So you apply it to Scramble, you get another function, okay? So this output's not very helpful, but just now look at what happens. When letters, if you do, so before we were, so let me just just to emphasize. So before we were doing that, now what we're going to do is transform Scramble. So there's going to be another function, and then we do apply it again. Oops. And now it prints out each step. So the first step was Scramble, pick 5, and the next step is paste them. And run it again, does the same thing. So what's happening is, if you look at this stepwise, so let me bring up the definition. It was this, right? So if let's print it out stepwise. So the crucial thing is the first thing, the L applied. So what happens is you put that dot, so if you look at the L applied, that dot's going to be a function that you put in. You apply to that function this composition operator, and then you apply print to it. So basically what's going on is when you type stepwise Scramble, okay, so let me make that. So what you're actually doing is you're doing the sample, you're doing sample and then printing, and then you're composing that with paste, collapse, and then you apply printing at the end. Okay, so now if I put in, say, the letters here, now I use a pipe, and I, apply that vector to this function, then you get the steps. You see what's happening? So what it's doing, so this is kind of like the first interesting things. This function Scramble, it's a function, right? You could do letters. It has parts, right? It has the 2 parts. And so it's kind of like a list, right? In fact, you can see this 1 and the 2. It's sort of purposely like what you would see if you print out a list, right? If you print out a list, it prints like 2 components like that. So this 1 and the 2 is very list, those are list components. So you can act on the function like it's a list. So I can do, for example, Scramble. Let's take the first function. That's going to just be the Scramble. The second one is going to be compose, right? Scramble had these names. Oh, actually, I didn't give any names in this case. But anyways, you can do things like you can scramble. You can just run the components in the reverse direction. So you see now the first component is going to be paste, and the second one is sample, right? Because what did I do? I just reversed it, 2 to 1. So you get all these operations like subsetting. You can even do things like I'm going to take the first, so let's say the second thing, and I'm going to make it say just paste, okay? So now when I scramble letters, say size 5, what does that do? I think it puts spaces in between them. No, it just spits them out again. Okay, so that's just a little example of like how does that work? Is that clear? It's doing, you just compose things. But the key is you get a composition, but it has a structure, right? It's like a chain, and you can, it's It's kind of like a list. So writing sample, whatever, paste, you think of this as writing something like list sample paste. Okay? So in fact, I could, if I just apply compose to that list, in fact, I'll get it. So it's sort of everything, like this intuition of function chains is kind of like chaining things together like lists, so they act like lists. They do behave like that. They're not lists, but you can treat them like that. Okay, just one other like real quick example, because this is kind of fun. You can even do very sophisticated things very, very concisely if you're not always trying to track this like x or this point. So for example, you can like tabulate primes very easily. What you do is you just take, say I want to do something like primes 10 or 100, and I want that to print out like the primes up to 100. So the one way you can do it is you just take, let's do it like this. I'm gonna build it up in pieces. So I have the first part, which is just take a sequence of things. Then you cut off, then what you do is you cut off the 1, so you take the tail, right? Okay, so now I do primes of 10, I just get to 2. And then the next thing you do is then you have to find out like which of these numbers are products. Oh, by the way, prime numbers are numbers which are not, they're only divisible by 1 and themselves. And the next step is you can do something like, well, I will have the range, and I want to find what are all the products of those numbers in the range, and that's this operation called outer product. So it's this operator. If you've never seen this percent or percent, then look it up. It's quite useful. So if I do primes 10, then it will compute the range in this matrix of outer products, and then the only thing I need to do now. So you see how I'm building it up? I'm like starting with bit by bit. I'm just building up the function. Now I'm going to compose the last part, and it will be take the range and the products. And so I take the range, and I want to filter out the range, those things in the range that are not products. That's a prime, right? So that's one way to compute prime. This is not very efficient, but just to give you an example. And then if you want to see like, okay, we did all this stuff, what did we do? And you just print it out. And you can do all sorts of things like cutting and cut this function and just look at what happens when you do a point. Yeah.
You removed the first element twice.
No, did it? Oh.
Is there a way to
Oh, I see. Oh, okay, let's just do that. So the primes 2. Okay, so I got rid of it. So it's gone now. You can just like kill, it's like how you would kill things in an environment, I think. So you just kind of like guess like what it will do based on what you know with lists, and typically we'll do that. Okay, so that was just like a little taste of what's going on here. Okay, so like I said, I just want to do a little fun examples. They are mostly not my code, so that's the real part. I didn't write the code, so I guess it's real. The other one, so the next example is the game of life. So the game of life is, it's what's called a cellular automata. Let me just run the movie to show you. So what's happening is you have this grid, these squares, and there's kind of like evolving. And the rule is that if you, so the yellow is like the living things, and it's changing and they're growing. If a yellow square is surrounded by nothing, it dies, lonely. And if a yellow thing is, little cell is surrounded by too many yellow things, it also dies, it gets suffocated. And there's kind of like a Goldilocks number of neighborhoods, and then a yellow cell will persist. Also like an empty area, blue, if a blue is just surrounded by a sea of blue, no life can arise. But if a blue is surrounded by the right number of yellow things, then it will kind of like come to life. And so that's kind of the rules of the game. And it just keeps going on like this. And it's sort of like in Space Invaders, if you go to the right, it comes out on the left, and you go to the top, goes on the bottom. So how does this work? So the way this thing works is, so it does this. This is, so you take this omega, which is this. Okay, just kidding. So this is, this code is, this is not R, this is written in a language called APL, called A Programming Language. And R takes actually a lot of inspiration from this language. Now, this kind of code is basically inscrutable. But if at some point you kind of like understand something, there are a lot of interesting ideas. So the example I want to do is I want to take this code, or like the idea of this code, and show how you can like implement this game basically in like 4 lines of code. It's very simple. And the point is like, the goal is not write short code, because short code is never the goal. You want your code to be readable, and ideally it should be fast, but brevity, just for brevity's sake, is not what we're aiming for. Okay, so, all right, game of life. So how does this work? So this is the next example. So here, so let's see. Okay. Oh, by the way, is this, okay, is the size okay? Like it's defined as readable? Okay. Okay, so the way it works is you make this grid, it's a matrix, it's a Boolean matrix, right? Yellow is true, blue is false. So I prepared like 2 matrices here, so one called cells and world. So if you look at cells, it's this, and world is some bigger thing. So I made some little utility functions to plot this, because looking at this doesn't tell you anything. So we can just show cells, it's this matrix, and show world, and it's that thing. It's basically the same one, but embedded in a larger world. Okay. So how can we like animate this thing? So to do that, so I'm going to let you in on something that I did, which is maybe a very bad idea. Like before I was setting up my computer, I actually had the code for this here, and I deleted it. I thought it'd be funny if I could just try to recreate it. So it could be that I get stuck. Well, let's try. So there's a number of helper functions. So I just wrote this ahead of time because it doesn't add anything to the talk, just to do these by hand. So just let me explain what's going on. So you have this, you start a configuration, and you had to find out like what are the neighbors of all the points. And the basic idea is the following. You take your starting configuration and you translate it in all the 8 directions. Okay, so there's one function that will specify all the directions. That's something called, that I defined here, it's called square. Okay, so you give it okay, let me shrink this down here. So you give it like -1 to 1, and it's just going to give you all pairs of numbers from -1 to 1. So that will give you like all the sort of direction vectors for the neighbors. And then there's a function called translate, and it will just shift an image around. So for example, if I translate cells by the vector like 1 down and 1 across, okay. Oops. Let me do the other one. Let me do world, and then let me show world. So watch carefully. It's going to move. See, it moved. Right. So this translation does this moving. So the logic is this: you just take your initial configuration, you move it around, okay, in all the 8 positions, and also the starting position. Then you just add up how many neighbors there were. And that should determine the rule for the next step in the evolution. So how do we write this? So it's a little bit easier if I switch now to here. Okay, let me go open up a new window. So this life thing is going to basically have 2 components, which is one is you let's see, I guess you count the neighbors. So I don't know what that's going to be, but let's just fill it in with some dummy function. And then you count the neighbors, and then you evolve. I don't know, just making up a name. That's basically roughly how it's going to work, right? You count, Based on the count, you evolve. So this is life. It just has two parts. Oh, I didn't. Oops. So it has these, two parts. It's just the identity function. So what we're going to do is, we're going to just like what we were doing with the primes, just like fill in the pieces. So it's kind of like scaffolding. See this thing? We're just like hanging markers there. Okay, so right now, for example, if I look at life evolve, right, so subset the name, it's just nothing. Well, it's just an identity function. So the first step is, so let's try to figure out what that first thing is. So life count, so we're going to assign it the function that basically takes your cells, okay, as the first thing. And then it's going to count them. So it's going to do some, you're going to have to apply another function to the cells. So like something like, I don't know, call it count neighbors. Okay? And I'm going to, I want this to be a composite function, so I'm going to apply a trick where I can just compose against null, and that will just make a composite, composite function. So that I can use this magrittr-like syntax. See that dot? That's like the magrittr dot. It's a dummy. Okay? And it's the same rules. The magrittr rules for how the dot behaves in the magrittr prior to. For example, if you're familiar with those, if an argument matches a dot exactly, then the dot, you don't have a dot as the first argument. Okay? So if you look at life dollar count, it's just that one function. Okay. Now, what is the count neighbors? Now you have to count the neighbors. So, so the second part is going to be count. You're going to do something like this function will be, well, you. Okay, let me use the same syntax. With, so we have a list with names, and in that context, we want to apply the logic of the game. So there are these cells and the count of the cells. So the rule for this game is if the count is 3, you live, okay? Or if the count is 4 and the cells are alive, you also live. So this second line is the rule of the game, and then I compose again with null. Okay, so now what you have is, if you look at life count, the second part, it's just this function that, see with the width, you see this little dot here, it just got inserted. We didn't write that, but it got inserted because that's the syntax for the pipe operator and therefore also for the compose operator. Okay, now if you run this on the cells, okay, great, let's do it. Okay, oh, why doesn't it work? Okay, well, something's not working. Well, actually, if you look at it, it's this count thing. We never defined it. So now we have to define these. How do you count the neighbors? But that's what this picture was showing, right? You just like translate the square around, and then you just count them. Okay, so you do, so this count, or what did I call it? Let me just copy and paste it. Count, oh, by the way, so let me write it like, just so everything fits on the line, let me write it like this. So count neighbors, what you're going to do is you take this square, like all the directions, that's this square, right? So if I write the square, these are all the directions. So I'm going to I have to map over the directions and translate. So I just literally write that out. So I map over the directions, I translate it, and translate is a function that translates x by a certain amount. So the thing that I'm translating is the x, and I purposely put it in the second place so that I can just put a point here. And then the next step is we just add everything. So the way you do addition, of like a bunch of matrices. You can't apply the sum function. You have to do a reduction with plus. So you reduce with plus. Okay? Does that make sense? Is that kind of close? So look at, okay, so let's look at it again. So count neighbors is also a composite function, and it has two parts. One is you map over the directions. You map translation, the function over directions, and you translate the dot, which is the thing that we're going to feed in, the cells. And then you just add everything up, because it's a Boolean matrix. So when you add, it gets coerced to integer, and you get the count. So now if we, so everything, so we have all the pieces here, right? Oh, except the evolve is, oh, that's why it didn't work. So life evolve has to be, let me just write it out quickly. Cells is 3, or cells is 4, and no, not the cells. Let's see, what were we calling it before? Okay, so all, the order got all screwed up. So let's do it again. So let's start. Okay, so count 1. Okay, so this, yeah, so this is live coding, so that always happens. So the first thing is you need to count things. So you collect the cells, and you take the count of the cells, which is this count neighbors of the cells, and then so this we called count before, and then the next thing is we want to evolve. Okay, just giving it a name, and it was this width. Now I'm just going to copy and paste it from here. Right. Okay, so life now has the 2 parts. Now this has too many parts. Okay, this is great, because we want to get rid of some of this stuff. What are we doing in the mind? So we take life, count, we want to get rid of that, so just get rid of it. Okay, so we got rid of it. Now the names are kind of messed up. Oh, I got rid of the wrong thing. Oh, okay, so count, evolve. Okay, I want to get rid of that. No. Okay, let me just do it from scratch. Sorry about that. I think I pasted that. All right, okay, so this should be okay now. So let's see. Right, so now this is what we want. First we want to count, like this. So look at the first function, just counting things. Oh, why is it called R? Okay, so we have to, sorry, I have to do one thing here, which is, okay, so here, so this is actually good that so many things are going wrong, because you can see how to fix it. So what I want to do is, I want to take a function, and I want to call it, so the names have to match. So I have to call cells, the dot, and count has to be count neighbors of dot. Okay. All right. Okay, that should work. So see, this name here has to match this because we are applying width. Does it make sense? Okay. So width basically just assumes these names in the list. Okay, instead of writing $signs, you can just write the names. So okay, let's try this out on the cells. So it sends everything to 0, which is a little bit strange. Let's try that on the world. Let's look at what it is. Oh, that worked. Although I don't know why it did. So let's apply it. So let's do this. So we take the world. Let's apply one iteration. So that's that. And let's do another one. That's that. And do the next one. Okay, and it goes and so forth. And I have a little function that does an animation. Nope. I thought I did, so I guess I have to. So let's, okay, so beforehand I made a little animation function. Basically what it's doing is it's just going to apply this life function again and again and again, and then keep displaying these things. So if I now animate the world, then it should start doing those. So it's just applying life again and again and again, and it just repeats. Okay, so there are a lot of little bumps in the road, but the point is not like get things right the first time. It's just sort of see the flow. You can kind of like build things up in pieces, and things can have names, and you can inspect them. Just so that we can move on to another more interesting example. This is kind of isn't the end of the thing, because now you see the output, but you might want to know like what is this counting actually doing, and you can see that. I just do. Oh, I have to. Oh, shit. Okay. Okay. So just to show you. Well, that's too bad because I deleted the function. Okay, let's just move on to that example. I'll just say it in words. So I send pictures like the logic is you move this cells around and you count. So I just said that and I implemented it. But you never saw directly what was happening in the intermediate step. But in fact, if you write out your function in these composable pieces, you can kind of short circuit it. And you can just say like, just show me what the first two steps are. And so you can inspect the steps in between, kind of like what we saw with the scrambling. Okay, so that's how this little game works. Okay, so, oops. Okay, so next example is, oh, I did the demo, is something with traveling salesmen. So that's all of these, none of these are my examples. I just sort of took them and then repurposed them for illustration purpose. So this example is an image, and then what you do is you transform it into one of these illustrations. You ever see where you draw a picture with a pencil, but you don't lift the pencil off the paper, and it's like all this squiggly mess? So you can kind of compute that, and what you do is, so it's this amazing little program by this guy, Antonio Sanchez Chinchon, I guess. What he did here is he took that picture, sampled a bunch of points, basically the dark points, and then found a path through all those points, like a single one path. And it's what's called traveling salesman problem, where you have a bunch of points and you want to find kind of like a shortest path that will go traverse all those points. So that's what's happening here. Okay, so this is an interesting example of where I took just to show you like how to, so that life thing we did from scratch. Well, what if we took like someone else's code that doesn't use this composition? Like how can it be transformed? So that's this thing Frankenstein. So this code here. So let me just run it. I believe it should, okay, if I run it like this, it takes like a minute. It's doing, you'll see in the plot window, it'll come up. It's just doing what I said. It just samples points, finds a path. Every time you get like a slightly different picture, it's doing random sampling. Okay, that's done. No, let's print it out. So that's what it's doing, okay? So it's these little points, and then finding a path through it. So this is an example. Okay, first of all, it's like a really cool thing, and secondly, like the way the guy wrote it is a very like standard way. It's like it's the way people use pipes. And one issue with the pipes is that you can get very long. That's not really the main. The pipe is kind of a nice arrangement, but here's the one problem with the pipe. That nice chain that you can follow from left to right, that's wonderful, but it's sort of frozen in your source code. You can't do anything with it. It's just a way to write source code. It's not a way, you cannot act on that structure. It just, the pipe just consumes it and then produces a value, okay? So let's do the following. So I'm going to show you how you can, let's try to do this together. So I probably will get something wrong, but show you how you can take this transformation of values and turn that into an operation by a function. So you'll see how this sort of the syntax between the composition operator and the pipe match, and also how you kind of change your perspective a little from values to functions, okay? Values to functions. Okay, so the one thing is, so we're going to need, so I'm just going to go here. So this is like one of those TV shows where someone goes in someone's house. It's like a makeover. I'm going to change everything up. It's like messy, but in the end, everything is nice. So if, Antonio, if you're watching this, awesome work. Forgive me for this, but it is for illustration purposes. Okay, so let's do a fresh start. I'm just going to restart the session. So I'm just going to load. Okay, so up to this point, I can just run that. That's just loading libraries. Okay, this part, so this is what, let's go through the code really quickly. So what's happening is this data, I'll just explain what's going on. The data, the main thing is this thing sample. Take a picture, basically like it's a huge matrix, sample points, you get a table. Okay, so this data is going to be the table. Next point, next step, take this data and then, so these points, and then find a path through the points. So it's called solution, but somehow it's like computing roots. Okay, this path. Then the next thing is, order the points according to like the ordering in the path. Okay, so I'm going to take a data frame and then I'm going to subset the rows by this thing called solution. Okay, and the last thing is just the plotting. So the last thing is not there's nothing. You have a data frame of points, and you're basically joining up all the points. Is that clear? Like whatever the details are, that's basically what it's doing. Now, the one thing you should notice is there are all these comments here, and comments are wonderful, but actually you don't need them. Wouldn't it be better if your code actually tells you what it's doing and you don't have these comments around that? So we already saw that before. And so what I'm going to do is we have this image. So first thing is that get rid of that line, because that image was the dummy, like this dot, this x in the pipe. That's just a dummy variable. You don't need it. So the first thing is find a name. I'll call it like sample pixels, because this is what the first step is doing. So it's sampling pixels. The next thing is you then change all of these pipes to these compositors. Okay, this is very mechanical. I could do search and replace, but let's just do it like that. Okay, and then there's like also we can structure like let's give this thing a name. This is called grayscale. This second part is threshold, so just give it a name. Let's just give it a name here. And then the last part is sampling. So you actually do the sampling, and let's just give that thing a name. Okay, let me kind of prettify that. Okay, so the structure is like that. Maybe put this on a separate line. You see what's going on? I'm just giving it a name. So it's the same thing. Pipes go to compositors. I've sort of grouped things according to what they're doing. So we don't need this comment anymore because I already annotated it. So if you run this function, whoa, what the hell? Oh, syntax error. So something is not lining up. Imager, we don't need that anyways. I'll get rid of that. Okay, that's more cosmetic. It's let's go. Okay, that's good. I don't know why it didn't work. So let's look quickly at sample. If you print out sample pixels, it's going to be some huge thing, a lot of parts, a whole bunch of parts. But you can look at the names of sample pixels. It has like this grayscale threshold sample, and the first part is this just taking grayscale There's two parts to it, or just one part to it. Okay, so that's the first part. We're actually done with that. So that's finished. Let's go on to the next one. So the next one is now it's called solution, but what we're doing is now we're finding the root. Right, you got the points, now find a root. So let's call this root. Okay? And this data is a dummy. Now let's get rid of it. Because this is the thing you put in. And actually what we're doing is first we're computing the distance, and then we're applying this traveling salesman's problem algorithm. So we get rid of this here, and everything gets changed to this compositor and as integer. And yeah, if we want, I guess we can annotate this, but just let's leave it like that. Okay, so that's a function. We don't notice that nothing in here we have to change. We just change all the pipes. Syntax is the same. So now, so we got that function root. So like has all these parts to it. Okay, good. Let's go on to the next part. So the next part is where we are actually ordering all those points. So now we come to the tricky part, which is always finding a good name for things. And I don't know a good name for this, because we kind of like, I thought we already got the root. No. Are we going to call this root again? No, I guess not. So here's what we can do. You know, when you write a function, this is very common. You write like make a whole bunch of assignments, do stuff, right? It's very typical. So you can do the same thing here, but without writing function. Just, you know that block where you make all those assignments? That's basically a local environment. You can capture that as a function. So in this Gestalt package, you have a function that does that, and it's called let. So you could do things like the following. I'm going to let, so the pixels equals, so the image, so we start with the image, okay? And so what you should be thinking is this. It's as if you're writing a function like, and I'm making assignments. Like I'm doing one assignment after another. The next thing is that you find, you sample the pixels, right? So we did this by sample pixels, the image. Okay, so this image is that image there. Notice that I'm putting a dot in there. And then the next step is we calculate the root. The root is just going to be the root of the sample, right? That's the next step. And finally, we make the picture. So let's call it picture. And picture is doing this thing. So that kind of solves our name problem. So what we do is we take the data. Data was the what we got out of sample pixels. So it's going to be sample, and the solution was what we call root. So we just do this, right? Okay. So let's call this I don't know, portrait. Okay, that's what we're going to get at the end. And this is going to be the first part of a composite function. So we're just going to, just sort of like what we've been doing all along, is sort of like dummy. Just we have one part we should know, and something else comes later we don't really know. So actually we know what's going to come next. We're going to plot. So let's just call it plot. And let's just put, let's just put the identity here. I don't know what else to put in. Okay. So you don't have to know everything ahead of time. You just kind of like, as you figure things out, you put them in. Okay. So what happens if we do a portrait of the image that we start out with? So remember, image is this image of the Frankenstein. And if we do portrait of the image, it didn't actually, it just prints out like what the computation is. It doesn't actually do anything, it's lazy. So it's just sort of like showing you what you want to do. You intend to do this. So you intend to do take image, sample, compute a root, and compute a picture. But nothing actually happens. Okay, because if you look at portrait, the second part, plot, is just identity function. It's not really plotting. Okay, so now we have to actually do the plotting. So just like there's let that like bundles all those assignments, the like lazy assignments, there's the, once you have those assignments like in a function, now go do something, like make that picture. So, so there's the once you do that, you run it. So you let image equals this, sample equals this, and so forth. Take all of that stuff, and then run. So it's called run. So you, so portrait, what we're going to do is we're going to take the portrait. So we just want to change the plot part. And we're going to make it, okay, let me do it, because I'm going to need, actually, let's just do it here, because it's already done for us. So that's all this part here. So you can get rid of all of that. We already, so this data solution, that's sample root here. So you can get rid of that. And this plot part is basically this. So let's just write it, put it in there. Okay, that's it. Oh, okay, and that's not going to work. So we have to run the thing. So so let's make this pretty. So what run's going to do? What do we want to run? Data to plot? No, because data to plot is not an object that exists anymore. That data to plot was this picture. It's a data frame. So we want to plot the picture. And then everything is the same. So the x and y are names in picture. Okay, well, maybe this will work. Let's try it. Okay, so, okay, portrait. So everything is done. So, so now let's back up a bit and let's recap what we did. Before we have nothing is computed here. These are just functions, no values. Okay, there's no data. For any image, this will work. For any image, if it works at all. For any image, it will work, or if it will work for no image. Let me do something. So we defined all these. So we just took each of the steps, converted them to functions, and then now we have a function that has two parts. It just takes everything that we have. This is the business logic, and then plot it. Okay, so let's try that. Portrait. Okay, so if it works, it will like take a little time, and then like either it will keep going forever or something, or we start. Okay, I'm gonna drink some water. Good. Okay, it worked. Great. Let's see. Let's try another. So I downloaded. So Art Studio has a terminal. I had an Elvis picture. Elvis, JPEG. Okay, I guess I could copy it here. Okay, let's try that. Now let's go back to the console. So let me do portrait, load image, Elvis. Oh, there it is. Okay, I believe this won't work so well, but it will do something. So we'll try. See, like, okay, work for Frankenstein. Maybe I was hard-coded. Maybe not. Let's see. By the way, you have no idea what the Elvis looks like, but I think you can get like you can see what that is, right? So let's see if that works also for us. Yeah, it kind of looks like Elvis. So let's see, if I, just to show you the original, where's the Elvis? What's that? Right. So, and you kind of see this. Okay. All right. So just to recap, so what did we do? Almost nothing. Okay, this is the thing. Almost we did nothing. Almost. We just like changed these pipes to these compositors. We took these comments and we threw them out. We didn't throw them out. We replaced them with names. A name is a kind of a comment. Nicer than comments, you can actually like subset this function on that name. So it's even more useful. They're like reference points. This part here, so normally you would have written this function like this. You would write function blah blah blah, and then image dot sample the and so forth, and then plot, blah, blah, blah. So that's fine, but realize if you do things, basically you're locking all of your logic and your computation in the function. You can't go in and pull something out. So for example, in this portrait, right? So you write a function, all that logic, that's just in there, trapped. And you have to copy and paste, go in your editor, change things, create a function, do things, start over again. That's very inconvenient. If you write the function portrait like this, it has the two parts, right? The first part and the second part's plot. So there's the second part. So portrait plot was the plotting part, like this ggplot stuff. You can do things like, you can understand what's even going on here. So for example, wouldn't it be like, you just see the finished result, okay? In anything that you're doing, any kind of analysis, the finished result is almost never the most interesting thing. You want to see, well, okay, it's typically interesting, but you also want to know, how did I get there, and is that correct? How can I know it's correct? So you always want to have some way to inspect. Now, typically, you just look at source code, you kind of like do some kind of ad hoc copy-paste and inspect objects this way. But because this function itself is decomposable, you don't have to cut away your source code. You can just cut this function and run the function. So for example, this is like tracing out this curve. Where is it starting? Do you know? I don't know. Hard to tell. And like, what does it look like to do like 2,000 of these points? Right? Or like some smaller number of points, right? So what you can do is, I don't know if I have time for this, but see, it's this number here, 8,000, right? Now, this 8,000 here is, but you can imagine this is something that you can, this 8,000 becomes a number like n points, and then you vary n points, and then see how that thing works then. And do you want to try that? I actually never tried this. I'm sort of just like, yeah.
Can you like unit test each little piece by calling just that?
Yeah, so you can do that, sure. So for example, this portrait, so if you look at portrait, the first part, which was just those bindings, right? It has the image, the sample, the root, and the picture, right? So let's take, say, let's say, like, what is this root, for example? If we're interested in the root. Let's do this. So this will be an example of inspection. Let's see, what does the picture look like after 4,000 points? So it does 8,000. What about 4,000? So what you can do is, so we have to change this thing here. So, okay, this is going to be a little bit hairy. I need more space here. So, okay, I've never done this before, so let's see how this works. So we take the first part and we apply image to it. Okay, that's just what we did. Now what we want to do is we just want to take the picture part of the picture. So we take, run the picture, but maybe just take the first 4,000 points, right? Okay, and then let's plot that, see what happens. Let's just to do something, okay, let's try that. And then we do portrait, the portrait only works on something called picture, so we have to now pipe this into, say, like picture equals that thing, and then so now we're applying a value, so I'm just using the pipe, and now I apply well, the pipe is kind of weird, so I have to do brackets here. Okay, with the compositor you don't have to do that, but with the pipe. And then I take the plot, and then I apply it. So that should, I think that should make, no, picture not found. Picture, okay, so let's see what happens. So maybe this step is bad. Picture not found. Why is picture not found? Oh, there's the picture. Okay, it's going. Okay, just let me stop this. Okay, so we can take the picture, and let's take the first 4,000 points, and then let's plot that. So I believe this should not give you the first 4,000 points. So this is the Elvis picture that we're doing. So that was, is that 4,000? Okay, so, oh no, this is Frankenstein with the image, sorry. Yeah, so that's like part of the picture, you see? So no, it didn't start down here. So if you look at this line, it's like super messy. But the point is, here's the main point. We didn't know, I didn't change any source code. Everything that I need is there. Just go dig in and get it. So it's, this is generally like the flow for analyzing data. Okay, so I think I actually had some other examples in mind, but I think that kind of like gives a good picture of like what this is and kind of how you use it. So maybe, okay, there's another thing that I mentioned in the abstract called values as functions, so I won't go into that. But if you look at the README for the picture, there's an example there of even if you just want to use the pipe to compute a value, like one time, get that value, then go on, it's still useful to consider that as a composition of functions. And so the README sort of explains like, well, what you get out of that. So we skip that demo. Okay, so you can install it. There's a new version that's on CRAN today. And you can look at the repo, which has more examples, and post issues there. All right, okay, thank you.
Any questions?
Right at the very beginning,
Yeah.
we did a syntax where you had a function in parens, and then you like had a value in parens after it.
Yeah, do you want me to go back to that slide? Yeah, let me.
Yeah, my question, I think, is basically, like, is that an R thing or is that a Gestalt thing? Because I've never seen that.
This here?
No, I know what you're talking about.
No, you was actually in the editor. You did
At the end?
Is that in
Oh, in RStudio.
Yeah, it was like your very first example of code.
Yeah,
I figured out if you were doing an R thing I hadn't seen before, or if it's a Gestalt thing.
So I did, okay, so the examples I did were,
Oh, it may have just been an anonymous function I didn't recognize. It was too anonymous.
okay, so for example, you can do this, you can do these functions like this in magrittr. But this thing, okay, but you can't do anything with this, really. Like you can't, like it's always just going to be a function of the one dot. Actually, this works, but and why does that work? That's a little surprising.
Can you literally pull out like the first thing when you first started RStudio?
Yeah, but my RStudio crashed, so I don't.
Oh, that's right.
Yeah, but okay, was it something with the pipe or with the compositor?
No, there was no pipes involved. It was paren, something, close paren, and then you did open paren, a value.
Oh, yeah. So I did something like, it would maybe do something like this, or with sample.
Yeah, so right
Yeah.
there,
Yeah,
that is a magrittr, I'm sorry, that is a Gestalt thing, how you
Yeah.
get the value afterwards in the brain.
yeah. So because, see, this thing here is a function.
Right.
So now we apply the
It's
function to
like a
value.
reverse Polish notation type.
Yeah, so this is why, so the pipe, oh, okay, so here's, okay, so the main point. If you want to call functions, use the pipe. If you want to compose a function, then use this. So you can do this. You can call it like that. And then everything is left to right.
The way that you do that -2 on the right, it gets passed what's on the left.
Yeah, that's just regular calling.
You look at a lot of Tabulate early stuff like their implier. Like you can do row-wise of a function and print another function. It's the same idea as that.
Okay.
Yeah.
Maybe because I don't understand that is why I never understood it. I learned something.
Okay. This is really neat. I understand now why it's not composed. Why the operator should not be called composed. Because it's in the other direction. And it always,
Yeah.
like, in math, the function composition goes the other direction. And I never knew why. But I wonder if you, it never made sense to me.
Yeah.
And I don't know why is one way in math and why this way is better.
Yeah. Okay. So I show you very quickly. So the question was like, why compose from left to right? Well, one answer is because magrittr does it, but the actual answer is because lists go from left to right. So for example, if I have a function like I do absolute value then log, maybe identity just for fun, just another function. So 3 things like this. I could convert it to a list. I get a list, and then if I compose that, I should get back the same thing. So if it went in the other way around, then the order would be reversed.
Why is it the other way around in math?
Because okay, so let's look at this function f, right? It goes, 1 is absolute value, then logarithm, then identity. So if you convert that to a list, it should maintain that order. Absolute value, logarithm, identity. And then if you compose it, you should maintain that same order. So if I now compose it, I should again, absolute value, logarithm, identity. If it went the other way around, every time you do one operation and the other, you would have to reverse compose. It's very awkward.
I think I'm asking my question better, but
Okay.
I'll ask you later.
Sure, okay.
Anyone else? Here and there.
So this is a lot of fun. I saw you using the ggplot command
Yes.
plus. Do you see not having to use plus anymore to build
Yeah, so what I read somewhere is the Hadley Wickham saying something like the plus was a mistake. It was before, plus is a kind of historical artifact. It was before this pipe. The plus is doing pipe, but it only makes sense in the ggplot. So you cannot replace that plus with anything else. It has a special meaning. So the way the plus works is when you make a ggplot object, it's taking that plus and interpreting everything in a special ad hoc environment where that plus is doing composition. So you cannot, okay, I'll give you an example. If I do ggplot cars, all right, I don't know, is this how it works? And then plus geom points. Okay, that works. No, it doesn't.
The left side is not an argument to the right side. It's not where you're at.
Yeah, but if I do this, it doesn't work. So there was it's a kind of a nuisance. But it's probably going to stay like that forever because ggplot's super complicated. And
What if you use the compose operator in there?
I never did that. I'd probably do nothing, but let me try it. I have no idea. I think it will just break. Well, it made a oh shoot! It's Can I apply this? No, well, oh, I didn't know. Okay, maybe, good point. I thought it would definitely be garbage, but I don't know if this is garbage. It's just, do this. Okay, hold on a second. Okay, let's do this. Let's do this. Okay. Maybe something works, I don't know. Okay.
So, followed pretty well, but I got lost with the let. Why wasn't the let just more composing?
Okay. Thank you for this question. So the let, in my opinion, is one of the more interesting things, because what the let is doing is the following. So it's easier for me to write it here. So when you're writing a function like, I don't know, ... or like x, you do something like y is logarithm of x, and z is equal to, I don't know, x plus y, and then w is equal to, I don't know, y times z, and then finally you do w squared. Like a function looks like this, right? You make a bunch of these definitions. What the let is doing is like this part, so let me do it, let me put everything here in brackets. Whoops. What? Okay, never mind. I just use a space. So what the let is doing is it's capturing this part in the function and then taking it out of the function. So the point there is, so I could write something like y equals logarithm of x. Well, I just take the whole thing again. Oops. Okay, all these become equal signs. And I call this, in the package they're called contexts. And if I run this, it didn't work because of a syntax error. Oh yeah, thank you. So if I run this, I get this context, right? It's just like a names, promises, technically. If I run the context and I try to extract one of the names, say y, okay, it's not going to work because there's no x. But if I say like x is 1, and then now I run it, why did that happen? Oh, because, oh, that's something strange. Oh, let's try w. Or z. Basically what the context is doing is it's, you're going to go back here, is it's capturing all of this in an environment which you can move around and reuse. So for example, if I had another function like this, and let me call it g. Everything was the same except the last line was like w plus w. All this stuff is repeated. So capturing all of these assignments with a let, this context, just lets you repeat it. So what you can do is you can write, then this f, you can, instead of writing this, you would write, you take this, well this is not a function, but if I put a dot in here, say let's do it like this. And then if I compose it with run, that context, say w squared, okay? That's a function. And if I run that against, say, like y, then it should do y is 1, oops, this x. That's why it's, this is y. Okay, let me call that a dot. Okay, let me do it now. Then you just got to trace back, give you 4y, because y is 1, z is 2, and then 2 times 1 is 2, and then I square it and I get 4. But you see this, the thing is this context, this thing, that function. See that those local variables are not captured in the function. I can reuse it because I can just compose it with another function. So if I add the g, I can just make like G is going to be the first part of that. And then now I run like 5 times W. Okay, so 5 times W squared, say. So that should give you 20 on 1. Right? So you see what happened? The F and the F and the G have all the same assignments. And why am I repeating that? So let me just capture that as a function. And I repurpose that. So basically, this is what I meant in the beginning by chaining functions and also like composing, like how you write it. So this prose that you write in the function, that's actually decomposable. You just have to find like where are the boundaries of the chunks you want to compose, cut them out. They're like little tools in the package like let, run, compose. And then take those pieces and you can put them together. So it sort of modularizes these objects that are trapped in your source code. Does that just answer part of your question about the lets, like what it's?
Why would you just make a grand function that composes your first design and call that set? And why do you need the let law?
You don't. There's many ways to do it. You can definitely do it that way too. You can certainly. So the point of the let is so when you make assignments, so the point of assignments is exactly right. So I'm binding these names, and in the expressions that come after, I use those names that came before, right? So if you just take a bunch of functions and they have like some formal arguments that are some whatever names they are, then you have to make sure you are matching all those names. But if you're in a situation where you already know how things are lined up, then you can just pick the names that you want. So you're right that like each of these lines could be a separate function, and you can change things together. But look at what's happening. You're going to be collecting. You compute one thing. Okay, pass one thing in, compute it, get another one, carry those two things around. Put one, send the y to the z, get the z. Okay, now you have x, y, z, so you've got to carry those around. So you can imagine, even if you compose them in individual pieces where each expression is a little function, in the end, if the thing that you want to do kind of like uses everything, you got to carry all of those names around with you. And the let just lets you do it in like one call rather than like a whole bunch of nested lists or something like that. That would be another way to do it. Is that goes to your question? Yeah, okay.
Folks, we actually need to some space. So if you have more questions, come to the bar, it's Ride House, and ask all the questions there. Thank you very much.